Let's take a look at how a wave propagates over an infinite lossless line. Suppose we have an infinite line that begins at x equals 0 and extends infinitely in the positive x direction. The voltage wave propagating in the positive x direction is given by A times cosine beta x minus omega t. Now let's stand at a fixed position at x equals 0 and observe how the wave changes over time at a specific location in space. We can represent time using the horizontal axis with the scale on it as omega t. This allows us to replace the increase in time with an increase in angle, normalizing the time parameter. Since x equals 0, the wave observed at this position is a sinusoidal wave A cosine omega t with a phasor of A and angle 0 degrees and an initial value of A cosine 0 in the time domain. As time passes, the voltage wave at the x equals 0 position remains a sinusoidal wave with the equation A times cosine omega t. Let's now consider standing at a fixed position at x equals L and observing the variation of the wave in the time domain. At position x equals L, beta times L is a constant, so we can rewrite the wave equation as A times cosine omega t plus phi, where phi equals negative beta L. The phasor of the wave is A with an angle phi, which means that the voltage wave at the position x equals L has a starting point of A cosine phi in time. As time passes, the wave at the position x equals L remains a sinusoidal wave with the equation A times cosine omega t plus phi, which starts from the point A cosine phi and varies with time. One notable observation we can make is that a time domain voltage wave at a fixed position has a constant amplitude A that does not vary with time. Instead, it is the phase of the wave that changes with time as cosine omega t continues to rotate with time. We can now create a 3D diagram to better understand the wave propagation. The x-axis represents the position on the line, with the scale of each cell as a quarter wavelength. The y-axis represents time, and the z-axis represents the amplitude of the sinusoidal wave. If we stand at a position x equals L, we can observe that the phasor of the voltage wave is A with an angle phi, which starts at A cosine phi in time. As time passes, the wave continues to change along the time axis. This means that if we were to connect the head of the voltage wave at a certain position on the line to the tail cosine omega t, the wave would change over time. Alternatively, we can change the way we observe the wave by focusing on a fixed moment in time and examine how the voltage wave changes at different positions along the transmission line. Let's now shift our focus and observe how the voltage wave varies with the position on the line at a fixed moment in time. If we examine the wave at the moment t equals 0, where omega t is always equal to 0, the voltage wave has a value of A times cosine beta x. This means that the phasor of the voltage wave at different positions is A with an angle beta x. At this moment in time, we can observe that the voltage wave's variation at different position x is a sinusoidal and has an amplitude of A. Let's now shift our attention to a moment t equals tau and observe the voltage wave along the entire line, which can be represented by A times cosine beta x minus omega tau. At the position x equals 0, as t changes from 0 to tau, the angle of the wave rotates to theta. We can observe that at a fixed moment, the wave varies with position because beta x rotates with position, while the amplitude A remains fixed and does not change with position. We have already examined the voltage waves on a transmission line from both the fixed position but different time and fixed time but different position perspectives. Now we will explore the effects of combining these perspectives and observing the wave propagation.